Hey guys, this is Professor Janacek, and I want to go over an example of finding a definite integral using the definition of the limit of a Riemann sum. So here's our definite integral notation. Remember, that is the limit of this Riemann sum here. Now I do want to point out there are other ways of writing this limit of a Riemann sum, but they're all basically equivalent to this. The other thing I want to mention is, before we get started, since we're using a summation, there are some little formulas for summations that we'll need to recall. The sum of a constant, the sum of k, and the sum of k squared. And remember, for all of these sums, k is going from 1 to n. All right, so let's take a look at this example. We're going to integrate from 1 to 3 of x squared plus x plus 1 dx. Notice that our integrand, x squared plus x plus 1, that is our function f of x. Now, before we get started with this, we do need to figure out what is the width of each interval. That's delta x. We'll let delta x be b minus a over n. This is a common value. This is basically ensuring that we have equal widths for each subinterval. And then the x sub k stars, we have to pick an x value within each subinterval. We're going to define that to be a plus delta xk. So basically how we're picking our x values within each subinterval. Remember, the subintervals are of width delta x, so we start with our left-hand endpoint of the interval, which is a, and then add a delta x for each of the k subintervals. All right, so looking at these values, our a is 1 and our b is 3. So we can go ahead and determine delta x 3 minus 1 over n, which is 2 over n. Again, you could define delta x differently, but I think making them equal widths is a nice way to go about this. And then how to choose that x in between them, we're just going to start at the left-hand endpoint and then pick something that is a 1 width away. So that in this case, that is 1 plus 2 over n times k. Let's go ahead and combine these, getting a common denominator. That's going to be n plus 2k all over n, and that's what we'll use for our x sub k's. Again, there are other ways of doing this, but I'm going to go ahead and go with this particular k value for each of this x value for each of the subintervals. All right, so now let's go ahead and put this into our limit definition here. So we have the limit as n goes to infinity of the sum, k goes from 1 to n, of f of our x sub k stars. The special x values that we're picking look like n plus 2k over n. And then delta x there in the back is 2 over n. So now all I want to do is evaluate our function f. Remember, that is x squared plus x plus 1. Evaluate that at n plus 2k over n. First time it's squared, and then we just write the term itself, and then plus 1. But all of this is still being multiplied by 2 over n. Let's go ahead and see if we can simplify some of these terms. N plus 2k all over n squared gives us n squared plus 4nk plus 4k squared. All of that is over n squared. While I'm at it, I'm also going to go ahead and make note that I'm going to distribute this 2n as well. So that gives me 2n times that one. And then the next one, I'll simply distribute, again, that gets multiplied by 2n. And then the 1 here in the back also gets multiplied by 2 over n, not 2n. Oh my goodness. All right, I think we can simplify this stuff even more. So we have 2n squared plus 8nk plus 8k squared all of these terms are over n cubed. We'll go ahead and write each of them over n cubed, plus the next two terms we get 2n plus 4k. Each of those are over n squared, and the last one is just 2 over n. Now, it looks like we can actually simplify these. First one is 2 over n. The next one is 8k over n squared. Then we have 8k squared over n cubed. That one doesn't change. The next one simplifies to 2 over n again. And then 4k over n squared plus 2 over n. And I actually think at this point I want to go ahead and combine some like terms. Notice I only have one k squared term, so I'll start with that one. That's 8k squared over n cubed, plus, now the k terms, I have 8k over n squared plus 4k over n squared. Combine those, that gives us 12k over n squared. And then we have 2 over n, and 2 over n, and 2 over n. We'll combine those three terms and get 6 over n. Now, these are summations, so we can go ahead and write this as, instead of the summation of these three terms, we'll take the sum of each term. So we still have the limit as n goes to infinity of the sum of k as k goes from 1 to n of the first term, of the sum of the second term, plus the sum of the third term. Also, because I'm taking the sum of as k goes from 1 to n, we could actually factor out those coefficients. I could definitely take out the 8, but also notice n is just a number. These summations depend on k. That is the index here, so I can factor out the 8 over n cubed. For the first term. For the second term, we can factor out the 12 over n squared. And for the first term, I'm just going to factor out the 1 over n. I'll keep the 6 as my constant. You could factor out the 6 and just have a 1 as the constant. Either way is acceptable. So now what we're going to do, still have this limit notation, but now what we're going to do is we're going to evaluate these summations. So I've got the sum of k squared, the sum of k, and the sum of a constant. I'm going to use these summation formulas that we have here at the top right to rewrite these. So we have 8 over n cubed times n times n plus 1 times 2n plus 1 over 6 plus 12 over n squared times n plus 1 over 2 plus 1 over n times 6n. Well, if we simplify this a bit, I can reduce an n. I can also reduce the 8 and the 6. That gives us 4 times n plus 1 times 2n plus 1 over 3n squared. The second one will reduce the 12 and the 2 as well as reducing an n, so that gives us 6 times n plus 1 over n. And finally, in the last one, we can reduce the n's and we just get 6. Notice we did get rid of that summation notation, yay. We still have the limit notation though. I'm going to go ahead now and multiply some stuff, distribute some things. This gives us, what is that? 2n squared, 8n squared plus 12n plus 4. Each of these, and take your time with that multiplication. If you need to multiply out the two binomials, then distribute, go right ahead. You might need to take a few steps in order to combine like terms properly, but take your time with that. And notice each of these is being divided by 3n squared, so I'm just going to write that underneath each one of these. Plus, the next one will distribute out the 6, and that gives us 6n plus 6. Again, each of these terms is being divided by n, and then we still have our constant there in the back. I will go ahead and now reduce these. So we have 8 over 3 plus 12, no, that's going to reduce to a 4 over n plus 4 over 3n squared, that stays the same. Then this one reduces to just a 6 plus 6 over n plus 6. And I think now we are ready to take the limit. As n goes to infinity, notice anything that has an n in the denominator will go to 0. Yay! So that gives us 8 over 3 plus 0 plus 0 plus 6 plus 0 plus 6. Combine all of these together. Oh, let's see, that is 12, 24. 44 over 3, I believe. So it turns out the integral from 1 to 3 of x squared plus x plus 1 dx is equal to 44 over 3. Well, there you go. Enjoy.